Hello, everyone. Good morning. Thank you for taking the time to participate in this webinar. Today I'm going to talk about, electric power system and wildfires. But before I jump into my presentation today, I just want to provide a quick background of my research in this domain. I would say, among all different, extreme weather events like, tornado, earthquake, storms, hurricanes, wildfire has very unique dynamics when it comes to the power system. And the reason I'm saying that, because not only, power systems, get affected and, by wildfire, and wildfire kind of cause, damage to the power system, but, electric infrastructures, is considered as one of the cause of the wildfire. So as you see, there is a mutual interaction between or relationship between the wildfire and electrical infrastructure. To that reason, I think, the wildfire has very unique dynamics that is worth to be studied, further. So, to that end, my research in this domain has two pillars. One is that how we can, minimize the impact of the wildfires, on power system, by enhancing, power grid resilience. And the second pass would be how we can, minimize, the risk of the wildfire caused by electrical infrastructure. And that is more like in the domain of the power grid situational awareness. So my research in, power grid resilience is more theoretical. It involves, formulating the problem and then, solving, some sort of optimization problem to figure out what would be the best actions, pre, during, and post, fires. While, my research in, power grid situational awareness would be more, practical and experimental research, which we have recently, got a relatively good sized grant in this domain. And as part of that, we are planning to develop a new lab, which is kind of unique in the nation, and it's called, Power Fire Lab. So we are trying to combine, the medium voltage test rig with, fire combustion lab. So as you may know, OSU has very strong, fire program. So we have around multi-million-dollar facilities, to study, the fires and everything. And I thought that this is a good opportunity that we develop, a new lab with the funding that we got from the NASA and also the VPR office to be able to, study this problem, closely, with more experimental, I would say, data. Um, the second pass, which is more on the power grid situational awareness, is kind of aligned with one of Masood's, publication, which is trying to characterize, the risk of the fire ignition by power lines. But it's just, we are trying to, run some experiment and then learn more about the dynamics of the power caused by power lines. But today I would like to mainly focus on, enhancing power grid resilience, which, as I mentioned earlier, is more on, theoretical and mathematical, formulation and analysis. Um, so in this talk in particular, I would like to talk about, enhancing operational electric grid resilience against wildfire. Before I jump into, my presentation, I would like to provide a motivation behind, this topic. So as you may all know, recently electrical infrastructures have experienced significant damages and disruption to large fires. So here I have listed a few incidents that happened just in our state, Oklahoma. So many people may think that wildfire is just limited to California and maybe, Canada, but that's not true. Other states like Oklahoma also experiencing, a lot of, wildfire incidents. So as a matter of fact, we just recently, a month ago, we have had, a fire in our town, although, our town is a small town, but, we just had, experienced, such a wildfire. Still, there are some investigation that even the power lines was the cause of the fire, but many of our colleagues lost their house. So we just have experience of such an incident firsthand. But as we see, the number and severity of this future wildfire is expected to increase rapidly, and exposing significant populations and infrastructure to wildfire loss and services. So, and then there have been research that's showing that the climate change increase the risk of the wildfire and also the risk of the damage to the critical energy infrastructure. So that's why there is a need for electric infrastructure resilience enhancement in order to minimize, the impact on the customers, economy, and the system. So obviously there have been, significant effort, toward enhancing, the power grid resilience. So the utility companies, one of the pioneers and leaders in this domain, and they have done a lot of, I would say, measures to be able to enhance the power grid, resilience. So they have been trying to improve, their fire speed modeling and other weather, modeling application in order to be able to predict, such an incidents and plan for it in advance. And also, deploying, passive resilience techniques such as, undergrounding power lines, vegetation management, pole reinforcement, and other system hardening, methods. So, but the problem here is that these passive methods are really costly and require, time. So if you want to, underground, the power lines, definitely that would be costly. So there has been an estimation, in Oklahoma, if we want to do that, it cost us, around $58 billion. So, but fortunately, there are some other ways to minimize or delay, this cost. And that would be through incorporating, something I call operational grid resilience measures, or, sometimes I refer to it as an active grid resilience versus, those passive methods. So in this talk, I would like to focus more on this operational grid resilience or active grid resilience. But let's first, define that, what I really mean with operational grid resilience. So operational grid resilience, in fact, is through incorporation of a smart control measures into the operational procedures of the system in order to effectively, manage, resources and asset, during system operation. Okay, and that can be during or post fire. But what they trying to do, they try to push, the system to bend, not to break against wildfire, and obviously trying to minimize the immediate impact of the wildfires, absorb, or withstand, the impacts, and quickly recover the system to its stable state. Okay, and in other words, we are trying to survive a crisis as it happens. So there have been, a few examples of this, operational grid resilience. So as you all familiar with this curve, showing, the resilience of the system, pre-incidents, post-incidents, and, during the recovery phase. So for example, you can use or leverage some measures like system islanding or optimal dispatching of the power systems or network reconfiguration or something we call, public safety power shutoff, before, the fire happens in order to minimize the risk of the fires or get prepared, for the fires that may happen, soon. And when, that incidence or disturbance happens, again, you can, make some actions like again system islanding, optimally dispatch your resources, including VRs and energy storage, all those stuff, or do network reconfiguration, or shift the load as needed. And then during the restoration, part or phase, you can use some sort of optimization to figure out what would be the best strategy for load restoration, or as needed, you need to do rerouting the power, or doing network reconfiguration. Those are some examples. But the bottom line is that how, by incorporating some sort of smart measures and control, we can operate our power systems in a smart manner, in a way that we can minimize, proactively minimize the impact of the firefighting. So but so here there have been several challenges. So if you want to solve for the optimal grid actions, before during the wildfire, so you are facing several challenges. For example, you are dealing with the heterogeneous network topology of the transmission and distribution grid. You have maybe too many control variables, so the number and the nature of them, they can be continuous, discrete. You also have some physical and operational constraint as part of this operation, and you have a lot of system uncertainties that belongs to the wildfire behavior or the load and generation. Everything is kind of varied. So that's why, I argue that this operational grade resilience enhancement is a complex problem when you just look at it from the optimization perspective. Okay. And for that reason, the grid planners and operators are in great need of decision-making tools, that help them out, figure out what would be the best action, during, such an incident, and even before that. And everything, many times needs to, happen in real time, or at least they need to get, some recommendation and to act, quickly. And um, so that's why, we are looking for some sort of science-based solution that proactively can enhance, the electric infrastructure resilience, against wildfire. So my strategy, to tackle this problem is, in order to come up with an optimal solution, first we need to understand, the impact of wildfires on our system. Right? So that would be the first step for us to be able to come up with a good action list or a strategy to deal with this problem. So unlike many people thinks that, okay, the wildfire can only cause, damage because of the flame and when, when the equipment catch fires. But in reality, not, the wildfire has some byproducts, which a flame is one of those. But, it create, the wildfire creates, heat, it generates, smoke and ash, which all of these byproducts impacts on the power system operations. Okay? So that's, the first step for me is to better understand how the wildfire can impact on the power system operation. And, try to, analyze the impact of the heat, the smoke and ash on the power lines, transformers, switchgear, loads, and also, our renewable power generation, and try to mathematically formulate, this impact in order to be incorporated later on into our optimization problem, right? And then also, develop, some sort of stochastic, probabilistic, scenarios based on those impacts, okay? And then the next step would be developing, some sort of self-healing solution and mitigation strategy, try to come up with a set of, proactive operational action in the system to mitigate the wildfire impacts and, ensure the continuous operation of the grid. But, when it comes to this problem, is quite clear that you are dealing with, a non-convex problem, stochastic, with the stochastic behavior. You have a list of mixed integer involvement, and because of the nature of the wildfire, which is kind of progressive, so you may also have a multi-stage, optimization problem. So um, again, you can use the variety of techniques, like AI these days. Everybody is talking about the AI, but that can be a solution to how we can accelerate the process, and contribute to a scalability of the solution in terms of the computational speed. But So I would say, generally speaking, I would like to mention that, the wildfire is a very complicated, problem. And I guess, there have been, some efforts, to try to come up with, some sort of a strategy in order to improve, the operational resilience. And I guess in all of this, the people trying to, better model, the problem in their optimization. And, that's the object. And I guess still, there are room for improvements, a lot of room for improvement, and everybody's trying to contribute somehow from their own perspective. So my contribution here is to first understand, the impacts and be able to model that impacts, and also, trying to model the problem, as close as possible to the real world, situation. So I start with the impact of the wildfire on power system, in particular, the power lines, because normally, the power lines is, spread across, geographically, spread out, and that would be one of the most vulnerable, component in the power system to wildfire, and we would like to see, how that wildfire impacts on our power. So obviously, one of the way that the wildfire can, impacts on the power lines would be through heat, right? So, and how it impacts, on the power lines. So definitely the heat generated, or radiated or conveyed by, wildfires can impact on, the thermal rating of your power line. So in order to be able to mathematically formulate that, we are using, the thermal balance equation, which is kind of the first order differential equation, representing, the thermal balance in the power lines. And as you see, there is some, heat generated by the current going through, the lines, as well as, the heat absorbed by the sun, which is generally speaking, with, the heat dissipation of the lines through, the radiation or convection, and then, as well as, the change in the temperature of the line. So, in a steady state, we expect that the temperature of the line, remains the same. And so when you add, the impact of, the wildfire into this, so then you adding two, component, based on the way that, the wildfire can, transfer heat to these power lines, for example, through the radiation. And then, these two components are a function of, the fire geometry, in terms of the distance, the height of the face, everything, which, these sets of equations trying to, formulate, that impact, based on the distance and, of the wildfires and other geometric, parameters of the fire compared to with respect to the power lines, and then be able to, kind of formulate, the impact of the wildfire or the heat on the power line capacity. But remember, another factor that you need to consider here is that the resistance of the lines is also a function of temperature. So as you are adding, so as the temperature, of the ambient temperature, I would say, increases, then you also expect that this resistance will also change. So this is, kind of how, the heat of the wildfire can impact on the power lines. So the next slide is showing how the heat can also impact on power generation. So we all know that the output power of the solar is a function of the amount of the grid or radiance that it received from the sun, as well as the temperature. So as you increase the temperature of the solar PV panels, that definitely impacts on the efficiency of the solar panel, and that would be kind of degraded. So here we have been trying to formulate that impact, how the temperature of the panels may change due to irradiance by itself, and how that temperature can be also change based on the heat received from the wildfire, and how that impacts on your power generation. Okay. Um, the next things we need to consider would be the impact of the smoke on our power generation. So again, as we have smokes definitely in our area, and then we imagine you have the solar farm plant, the solar PV farm, then obviously you should expect that the output power of your solar PV panels get affected. But how we can model that? So we are trying to formulate this problem based on the absorption of the light caused by the smoke through something called the Lambert law. So the Lambert's law states that the absorbance of the light in the medium is directly proportional to the length of the sample in which the light passes. And then the Beer's law states that the absorbance of the light in the sample is directly proportional to the concentration of the sample in which light travels. So it basically depends on the length or the depth of the smoke, and also the density. So there is some sort of formulation that the environmentalists use to basically model the say the smoke concentration, and that depends on the rate of the burning of the material, surface area, some other variables, and then based on that, we can formulate how this smoke density can impact on the radiance received by the solar power. And as you remember, through this simple equation, we can somehow adjust the gradients received by the solar panels, get affected by the smoke, and then how it impacts on your output power generation. So another factor that impacts on solar power generation would be also soot and ash caused or created by the wildfire, burning the vegetations in the region. So again, as you so again, as you see here, based on the study has done, the extinction of the, light caused by a particle is a function of the particle extension, efficiency, or QE. But in this formulation, you have, M, which is basically the practical effective, index, and also, the alpha, which is the ratio between, the particle size and the wavelengths of incidence radiation, which basically defined, the effectiveness of this, so in order to, cause, basically extinction of the light. And then, another factor is, the covered area, okay? And that can be also calculated, based on the mass of, the dust and soot that you expect, generated, as part of, this wildfire. And, if you consider, the incident lines, comes with some angle, you can modify this equation. But at the end of the day, the irradiance received by, the solar PV power gets modified based on the extension efficiency and the area covered by this soot and ash, which basically kind of degrade, the radiance received by the solar. So all I'm trying to say, when something like wildfire happens, you may need to include all of the impacts on your power operation in order to be able to come up with a good solution. You need to understand that the capacity of line of your line may change. You need to understand that you might not have as much as solar power generation that you expect to have. And also, in the next slide, I will, before I, go to another impact, I would like to, mention this as part of our commitment, to involve, undergraduate research, so I have assigned, this part of the project to a few of, undergraduate students from the Northern Oklahoma College. So they are basically the first or second year students. And then, they have been trying to, basically experimentally, show how the smoke and the ash and soot can impact on the solar power generation, and then we will be able to kind of, verify our models. Again, this is very small scale, it might not be as accurate, as running this, at the larger scale, but I think that would be a very good practice for undergraduate students, to get engaged in the research and also, contribute to this research. So as you see, they create very nice chambers in order to, even, create some sort of a smoke inside these chambers and then expose it, to kind of the reptile, sun lamp to basically, emulate, a constant and not variable, solar power, radiance. And then they just, used, some sort of cork dust. First of all, they would like to see how solar power get impacted, if they, you have dust and soot, PV cells. And then also, they create, some sort of a smoke inside the chambers to see, how that impacts on the solar power generation. And as you see, they set up a very nice, data collection, I would say, system, the system for data collection, which include a Raspberry Pi and, interacting with the sensors, collect, the power generated by the solar PV under different, scenarios, and then they could, collect those data and then use those data for analysis. So another impact that I would like to discuss caused by the wildfire is also on the wind power generation. So the output power of the wind turbines really depends on the quality of the turbine blades and their surface area roughness. Okay. So when you have the soot or ash from the wildfire, it has the potential to weaken, the smoothness of the wind turbine blade. Okay. And that impact, on the power generation by the wind turbine. So here you can see, two graphs or charts, which basically explain, the effect of the dust on the power curve of 300 kilowatt, wind generators. And as you see, that power, it depends on, two factors. One is, the area covered by dust on the blade and also the thickness of the dust. Okay. So in the chart on the top, you see how by increasing, the dust thickness, the output power of, wind turbine gets degraded. And, also, how the area covered by the dust, in terms of the diameters, impacts again on the power generation by the wind turbine. So these are the factors that we need to consider. So now, I would say somehow formulate, the impacts of the wildfires through its different, byproducts on power system equation, at least, the key impacts, although, the impacts might be wider, than what we have done. But again, I guess those are the things that we thought it would be, essential, to be considered. So now, the next step for us is to formulate some optimization problem. So that's the second stage of the research. So as I explained earlier, so the first stage was, understanding the impact. The second stage is to, formulating the optimization problem in order to come up with, developing some decision-making tools in order to come up with some strategy dealing with the wildfire. So as you see here, so you see a list of, equations represent, the optimization problem or optimal power flow here. So as you see, we are trying, as part of, our objective function, we're trying to minimize, the load outage, based on, the priority, and also trying to minimize the operation cost. So, so before, I explain this optimization, so let me just tell you a little bit about, the controllable assets that we have in order to deal with the Wi-Fi, in the real time. So you can, control your power generation, including your DRs. When I'm saying DRs, energy storage would be also part of that, renewable energy storage, any other, generators, you may have micro generators. And at the same time, you can also control the switches in order to do reloading the power, reconfiguring, your power system. So those are, some sort of controllable assets for me to control, to deal with, the wildfire. But the objective is to minimize, the load loss, while you are also minimizing, the cost of the operation. So, and as you see, when I'm talking about this controllable asset, so you see that, controller variables can be continuous. Let's say you want to control the active and reactive power, of your DR asset, or you may also need to change, adjust the status of your control asset. Um, so for, for that reason, you have, a kind of mixed integer programming here. So I guess, we don't have that much of time, so I try to, probably move quickly as I have also another meeting, sharp at 12. Um, so, um, but the bottom line here is that, so you have a stochastic optimization. I mean, right? So that's why, we just include, the probability of, uncertainties in our system. That uncertainty belongs, to the solar power generation, the load changes, and also, the wildfire scenario by itself. And then, in this particular problem, we are targeting, distribution system because, generally speaking, the distribution system is the part of the system that is more vulnerable to the wildfires and is get affected by the wildfire by far. And then, as we see, we just, have some constraint like, branch flow, and then, the power balance, although we are trying to, linearize, this flow in this case. And then you have some physical constraint and also, some environmental constraint. And as you see, we have been trying to, also formulate the heat flux caused by the wildfires that we later on need to understand its impacts on the power lines, capacity and, the solar power generation. So, and this is how we just formulate, the power lines, get impacted by the temperature and its capacity, and then, we also, included, some sort of protection system that when, the temperature of some lines, exceeds some threshold, it automatically get disconnected. And that's, also impact, on your operation. So let's say, as part of the operation, you're also experiencing some sort of reconfiguration in your system. And now you need to rethink, okay, how I dispatch, my resources again. And then as I explained earlier, so we just, also formulate the impacts of the solar and impact of the wildfire on the solar generation and the wind power generation. But remember, also in this, optimization problem, we consider, the balance in distribution system. So that's another important factor. So as I said, we are trying to make our case as much as possible closer to real world and not arguing that this is the best and closest, to the reality. But that's, the effort that we are trying to do. And we are, as we move forward, we will see we are trying to improve it, even further. And that's the contribution that you as a scientist can make here, to make, the model more realistic. And, also we incorporate, all of these uncertainties, into the system. And this is how we just formulate the variation in the solar power, the variation in the wind power, and how that get also affected, the wildfire. And we try to generate some sort of more color scenarios, representing the solar generation, wind, the temperature in the demand, change in the demand, and also the spread of the wildfires. And then this is kind of showing that how our power generation also get impacted by the wildfire, and how that has been modeled here. And other factors that we trying to incorporate, so far, I explained that our objective function is mainly focusing on minimizing the loss load, as well as minimizing the cost of operation. So there has been another important factor, which is called equity and social justice. So as we are doing the load sharing, or doing the operations, so you expect that some area probably lose their load, as part of this incidence, but how we can manage the system that everybody have the same experience. So the burden will be distributed, across all regions. So that's why we just come up with, let's say, 3 regions in this system, and trying to make sure that each region have the same experience, in form of leveraging from the resources, and as well as receiving the same burden as part of the power loss. And then here, you can see some result, how that, adjusting, so this is, how we just formulate the problem as form of, the summation of multi-objective function in one object, in one line. And then how, adjusting the weight can, prioritize, the equity versus, the load loss. So we tackle the same problem at the transmission system. So in the transmission system, we assume that we have AC power flows. We have non-convex and non-linear equations. And then this time we are trying to model the problem in form of multi-objectives, because we believe all of the solutions which is a trade-off between equity and the load loss and cost can be a good solution. Really depends on your basically preferences. So that's why we claim that we need to end up with a Pareto, that everybody decide which would be the best point for their operation. So, and that's why, we just, formulate this problem in form of multi-objective problem. So this is obviously a multi-objective non-convex optimization problem, which, we cannot solve it with the convex optimization, techniques. So that's why, here we just use some sort of heuristics method. And, in order to solve this, as I see, we have the nonlinearity caused by the AC power flows. Again, we have mixed integer involved, because whenever you change or the one of the lines is get connected or disconnected, the topology of the system will change, and that impacts on all of your matrices, impedance and admittance matrices, everything. And that's why that also needs to be formulated in form of some mixed integer variables, and that makes the problem a little bit complicated. And then we use the Marin predator algorithm, showing that how effectively that can solve the problem, compared to the particle swarm optimization. I don't want to get deep into that detail. And then, so here you can see, some of the scenarios, in the Pareto curve that, we just discussed further in details, in this slide. But the last stage of our research, that maybe I just summarize it in 2-3 minutes. So Remember, when the, before the fire happens, one of in the real world or the common practice is that, the utility companies generally, do some sort of action to minimize the risk of the wildfire. And one of those actions is public safety power shut off. So they just, de-energize, part of the system or some lines. I mean, right? And then, but remember, when it comes to the wildfires, I categorize the wildfires to two type of fires, endogenous and exogenous. Endogenous is the one that caused by the power system. Exogenous is the one that, may cause, by any other factor. So by minimizing the risk of the fires, caused by, wildfires, you only deal with, endogenous wildfires. But, there's always a risk of having, wildfires because of the dryness, wind the speed, everything in your region, which you have no control on. But when you do, the PSPS or public safety power shutoff, so that basically limit your options, if the wildfire happens in the future, because you already energize, part of the lines, and so the decision making process will be different, and I argue that this decision making, problem, during the wildfire is get impacted by, your decision during, the PSPS stage of the pre-fire. So that's why, if you look at, the literature, you see, the many researchers, they study these two problems as two isolated, separate problems, which might not be realistic. So I would say, what I'm arguing, in a recent publication is that, the wildfire is kind of a progressive event. Am I right? And then, any decision that you make at this time, may impacts on, on your this decision in the next stage. So whatever decision you make in the preventive stage can impact on your decision during the corrective stage, am I right? And then the restoration stage. So that's why, we are dealing this problem as a multi-stage optimization problem. Now you can imagine, how complex the problem would be. So you have multi-stage optimization problem. It is non-linear, non-convex. It has, mixed integer. It is a stochastic. So you have all those, let's say challenges that you may imagine, we have in this. And if you can imagine, we have a large scale power system, then the question would be how we solve this equation. First of all, how we formulate the problem to kind of represent the real world scenarios, and how we can, deal with such an optimization problem. And, in the next few slides, I was explaining, how we deal with, such a complex problem, how we're trying to enhance, the speed and the convergence speed, of the solution, and how we can, improve the scalability of the solution applied to this optimization. So by saying so, I would like to conclude. And, before that, I would like to also acknowledge, my team. So my team includes, 5 PhD students, 2 master students, and a few undergraduate students that helping me through the research. And, without their contribution, this, research may not be possible. So by saying so, I would like to, stop at this point and probably give you a few minutes to just, ask your question. And I'm sorry, I expect to just wrap up in 45 minutes and give you more time for question and answer.
Thank you, Hamid. That was excellent. No, apologies is on our side to take a little bit of time to set this up. An excellent talk. Thank you so much. I remember once we were talking about you giving this presentation, you mentioned that you prefer to do it in 3 to 4 months from now because you don't have a lot of content yet. And then I'm just happy that I convinced you to present today, because then definitely we can have you 3, 4 months from now with the new. This was a lot, right? And again, thank you so much. I'm actually gonna let others to ask a question. I'll be in touch with you. I have a couple of questions and a couple of other points to discuss. I also have to run to another meeting like yours, so I'll open the floor to others' questions. Thank you so much again, Hamid, and I appreciate it.
You're welcome. So meanwhile, I just want to make an explanation. So on the second part of our research, which is more experimental, we are still waiting, to collect more data. And I would be happy to present, that part, because that part is also very interesting to me, involves, some sort of practical and experimental research. to figure out, as I said, it's quite aligned with one of Masood's work, published on characterizing, the fire ignition by the power lines. And that would be a very interesting project to me. But probably, I would be happy to, in the future opportunity also to present, some of our result and achievement on that piece, which is mainly focused on power grid, situational awareness.
Thank you, Hamid. Yeah, we'll definitely get back to you for that round. And is there any questions from the audience here? Thank you.
Dr. John Brown, there is a question in chat.
Let me just stop sharing. Okay.
This is not a question, probably.
Yeah, if there's no question, I can ask a quick one, Hamid, then.
Sure.
The impact, when you look into the impact on the impact of wildfire smoke on the output of solar panels, and I'm talking about the smoke alone, I'm not talking about the ash impact or the impact from increased temperature. Question number one is, so you have access to any non-publicly available data source for that, both on the smoke side and on the PV output side? And then also, did you look into how you might be able to separate the impact of clouds from smoke and how the two might be different?
So I would say not really. So our research would be, and I really would like to explore that further, in the larger scale setting based on, some sort of real world data. But, we have been trying, to, understanding, mathematically how, the smoke, based on its density can, impacts on the solar power irradiance. And we just, as you saw, we just, experimentally tested in a very limited space that I understand that the dynamics would be quite different, in the larger scale. But, that was kind of, a limited, study that we just have done in this domain. But, in order to, get the data, so I would say, probably we need to get access to, a whole amount of, data in terms of, the smoke density. Sometimes those data are available, sometimes they don't, and, the thickness of the smoke. So those type of things, I'm not sure if anybody is measuring that, but I would argue that probably there would be some, research oriented to that topic should be done, to collect the right, variables and parameters in order to do some sort of fruitful study, in this time. But we haven't done that, but we are very interested to doing that in the future.
Excellent. Yeah, thank you. Yeah, we can be in touch on that regard, Hamid. I'll send you an email. Thank you so much, everyone. I know we are kind of beyond the time. Hamid has to run to another meeting as well. So thank you again, everyone, for your participation. Hamid is a search away, right? So if you just search Hamid Nazaripouya, you can find his email. Reach out if you have any other questions, any other ideas to discuss with. And thank you again for your participation. Have a good day, everyone. Thank you, Hamid. Thank you, Hamid. I'll be in touch.
Feel free to just shoot me an
Thank
email
you
if
so
you have any
much.
questions.
Thank you.